This is the second half of Chapter 7 on solutions. The topics for Part 2 are percent concentration, molarity and dilution, and properties of solutions, which will include solutions, colloids, and suspensions, colligative properties, and osmosis. So we'll start with solution concentration, and we're going to start with percent. So mass percent, which is abbreviated M/M, is the concentration by mass of a solute in the solution. This is used commercially, used in hospitals. And in order to calculate the mass percent, you need to know the mass of the solute in grams divided by the mass of the solution. And you notice the mass of the solution is the sum of these two. So I can replace grams of solute plus grams of solvent with grams of solution. Now you have to be careful here because many times they will give you the solute and the solvent, and you have to know that you need the solution to actually do the calculation. You can also measure volume percent, and we do this if the solute is a liquid. And this is common, for instance, with alcohol solutions. You have maybe you might have some rubbing alcohol at home. That says 70% on it. So that means 70% alcohol out of 100 milliliters of solution. And so that 30 milliliters is probably water that's left over. We can also have mass volume percent, and that's kind of obvious by the equation here. So let's take a look at an example. So if I weighed out 8 grams of potassium chloride on the scale, and then I added enough water so that the total mass became 50. So that 50 now includes the 8 grams of KCl. So that's going to be the grams of solution. So if I wanted to calculate the mass percent, I write down my formula and replace the data, and I get 8 over 50 times 100. I'm going to get a 16% solution. Now it didn't matter that it was 8 grams of KCl. It could be 8 grams of anything, as long as it dissolves in water, and I would have got a 16% solution. All right, let's go through another example. So let's say we made a solution by using 15 grams of sodium carbonate and 235 grams of water, and we want to calculate the mass percent. So we want to copy out the data and label everything. So the mass of the solute is 15 grams of sodium carbonate. The solute is always a smaller mass. The mass of the solution, you have to add them together. Again, this is where people make mistakes, I know. So we get 250 grams. Write down our formula and just plug things in, and we get a 6.00%. So you multiply 15 times 100 and then divide by 250. Pretty straightforward. Right, now here's an application of that formula. Let's say you wanted to know how many grams of sodium chloride you need to weigh out in order to prepare 225 grams of a 10% mass sodium chloride solution. So you already know what you want the concentration to be of your solution. You already know that. And you already know how much of the solution you need. You need 225 grams of it. So the question is, how many grams of sodium chloride would you use? So we're given 225 grams of solution, and we have our percent, or known as grams of sodium chloride. So the first thing is to really take that percent apart. So percent means 10 grams of NaCl for every 100 grams of solution. Now we want 225 grams of solution, so that's going to be more than 10 grams of sodium chloride. Now we're going to use this fraction here as a conversion factor. So when I take my given information, the 225 grams, notice how I just multiply it by this conversion factor. And let me get my pen down here. The red color, and you see the grams of solution cancel out, and I wind up getting 22.5 grams of sodium chloride. So that's how much sodium chloride then I would weigh out. I would add enough water until the total mass became 225. All right, so here's one for you to try. Solution is prepared by mixing 30 grams of sodium carbonate and 235 grams of water. Calculate the mass percent. So these are the 3 possibilities. So I want to pause the video at this time and try this problem. Okay, here is a solution to it. So there's the problem again. So I want to determine my quantities of solute in solution. So the solute is 30 grams, and the solution is the sum of these two, because it's only 235 grams of water. So that's going to be 265 grams of solution. All right, my expression is my formula. And then I'm going to just plug in my data, and I get 11.3%, and that's the answer. So how did you do? Hope you got it right. Okay, now molarity is the next concentration value we're going to take a look at, and this is used for chemical reactions because you get moles of solute. So molarity means moles of solute per liter of solution. We can write it as a fraction, as you see there, right here. And let's say I wanted to make up 1 molar solution. So this is how we write molarity. We use the capital M for molarity because there's no symbol for an element with just an M in it. So 1.0 capital M means 1.0 molar sodium hydroxide. That's the word we use, is molar. And that means 1.00 moles per liter. Now, do you need a mole of it? Well, you do if you want a liter of it. So let's see, here's our example. So over here, let's say you weigh out how much a mole of sodium chloride would weigh. That would be 58.5 grams. That's its molar mass. And then we put it into this flask. This is called a volumetric flask. You see there's one little line up here. That's the only graduation on it. And then you add water until you get to that line, and that means you'd have a liter of it. And that's how you would make up a 1.00 molar, and there's the word down here for you, molar sodium chloride solution. So let's say we have a problem based on that. So let's say we have a half a liter of a sodium hydroxide solution, and we know that it contains 6 grams of sodium hydroxide, and we want to know what the molarity is. So copy out our given information. We have grams of sodium hydroxide, and we have 5.5 liters of solution. This is what we want. So moles per liter. So we need moles, which we don't have yet. We're going to get that. And we need liters, and we have that. So the molar mass of NaOH is 40. So that's sodium plus oxygen plus hydrogen. And then we get the molarity. So to get the molar mass, we're going to take my given information, and I'm going to multiply by 1 mole over 40 grams. That's going to give me 0.15 moles of sodium hydroxide. Now the grams would cancel out. And then I'm going to take my 0.15 moles of sodium hydroxide and divide it by my liters, and I get 0.300 moles per liter. Or I can write it as 0.300 capital M. And that's how you find the molarity. Now here's a question that's an application of the molarity formula. What if I have a certain volume of a solution, in this case it's 125 milliliters, and I'll say I know what the molarity is, it's 0.720 molar KCl. And I want to know how many grams of KCl are dissolved in it. So I copy out the given information. Right. Now in order to get grams of KCl, I'm going to have to find moles, because I can go from moles to grams then at the end. So let's see, I have liters in my molarity formula, and this is milliliters. So I'm going to have to convert milliliters to liters here. So to do that first, 1,000 milliliters per liter, and that gives me 0.125 liters. Now I can use my molarity here. Remember, this is a conversion factor. So I can take my number of liters and multiply it by moles per liter. The liters will cancel, and I get 0.0900 moles of KCl. I don't want to round that number off because I'm going to use it in the next step. Once I have the moles of KCl, I can multiply by its molar mass, which is 74.6 grams per mole. And that will give me my answer in grams, and I get 6.71 grams. So molar mass of KCl is, of course, the atomic mass of K plus Cl. Now here's one for you to try. What's the molarity of 0.225 liters of a KNO3 solution that contains 34.8 grams of KNO3? So pause the video, give it one a try, and then come on back and see the solution. Okay, here is the solution. Here's my question again. going to find the moles of KNO3. The molar mass would be 101.1. So again, that's potassium plus nitrogen plus 3 times the oxygen. So I'm going to find my number of moles. You see how the grams of KNO3 would cancel out. And I get that many moles. And then I'm going to take my number of moles and divide it by the liters, which I was given. And I wind up with my 1.53 moles per liter. Pretty straightforward. Hope you got it right. All right, the next topic is dilution. This is very common in all the sciences. We buy concentrated solutions and then we dilute them for our purposes. It's just cheaper and it's easier for storage to just buy concentrated ones. So in a dilution, we're going to be adding water almost always. And when we do that, the volume goes up, as you can see in our example here. Here's a small volume down here. See the line? Now we have a much larger volume. We've added a lot of water to it. And as we do that, the concentration goes down. Here you can see there's a lot more particles in a smaller volume. Here there's many fewer. So the concentration always goes down. This is one of those inverse relationships. So here's an example using orange juice. I guess you can still buy this in a store, though I don't think many people do anymore. Years ago it was very popular. So you can buy frozen concentrated orange juice. And actually they get rid of the water and then they can what's left. So look how they're very, very thick. And 1 can of frozen orange juice concentrate added to 3 cans of water gives you 4 cans of orange juice. And that's what it would say. So again, easier to store it, takes up less space, mix this up and then you'd use it. So in the initial and diluted solution, the amount of the solute, which can be measured in grams or moles, is the same. It's just the concentrations and the volumes that are going to change. So the concentration always goes down as the volume goes up. So percent, we could use C1V1 equals C2V2. C just means concentration, and V for volume. The initial would be the 1s, diluted the 2s. And for molarity, we would have M1V1 equals M2V2. Now technically, it's the same formula. And so we're going to be using these when we want to calculate or answer some dilution questions. So here's an example here. What volume of a 2% mass volume HCl solution can be prepared by diluting 25 mLs of 14.0 mass volume HCl solution? So I want to copy out the data first and label that. So let's get a better look at it. So what we're doing is we're starting with a very concentrated solution, 25 mLs of it. We want to add water until the concentration drops down to 2%. So let's look at the difference in the numbers here. 14 to 2. So that means that the concentration is going to go down 7 times. 14 divided by 2 is 7. So if the concentration is going to go down to only 1/7 of what it was, that means the volume is going to have to go up 7 times. So I bet 7 times this number is our answer. Let's just go through the solution. So here's my formula. I'm going to solve it for my unknown by dividing both sides by C2. So that'll cancel out there. Then I'm going to plug in my values. And what do I get? I get exactly what I predicted. Because you see down here, the percent would cancel. And the 2 would go into 14. 7 times, and 7 times 25. That's 75. So if the numbers are easy, sometimes you can see what the answer is to these questions. Now here's one for you guys to try. Let's say we have a 1% HCl solution. You want to prepare that from a 10% HCl solution. You're going to use 25 mLs of it. Oops, so we'll go back. So here's your problem. Give it a try. Come back and check your answer. All right, and here is the solution. Here's the problem again. Copy out the data and label it. So let's just look at the numbers. They're easy numbers. Here, 10% to 1%, so we're dividing 10 by 1. So if I divide 10 by 1, I should be then multiplying this by 10. I bet my answer is 250. So, I start with my formula. I'm looking for V2, so I'm going to divide both sides by C2. Like that. And then the C2 would cancel out. That's how I get over to here. Okay. Then I plug in my data, and I get exactly what I predicted. Okay, not too hard. All right, here's another one for you guys to try. What is the percent of a solution prepared by diluting 10 milliliters of a 9% sodium hydroxide to 60 mLs? So I'm just going to start you off with a data chart and have you finish it from there. So if we copy out the table, look what we have. Starting with a 9%, we're going to use 10 mLs of it, and the volume is going to go up to 60. So how many times is the volume going up? That's how many times the concentration will go down. So let's see if you can finish it off from there. So pause the video and then come on back and check it out. Okay, and here is the solution. So this time we're going to divide both sides by V2. So if I divide by V2 on both sides, here's my V2. I'm writing with the mouse, and that's not the easiest thing here. Sometimes it's easy, sometimes not so good. This is what we wind up with, and that's how we go over to here. Now I'm going to just plug in my data, and I get 1.50. So remember, and you can see that the volume milliliters are canceled, so this is like, say, 1 over 6. So the volume went up 6 times, so the concentration goes down 6 times. Well, we can do the same kind of questions using molarity. So here's one for you to try. What's the molarity of a solution prepared by diluting 0.180 liters of 0.6 molar HNO3 to 0.540 liters? Now you might think we have to convert liters to milliliters, but we really don't. We just have to have the same volume. So pause the video, come on back and give it a try. Okay, and here's the solution. As we compare our table, when we want to check it out, we can see that the volume is going up. So if you were to divide this into that, you see it come up 3 times. So the volume is going up by 3. That means this should go down by 3. So I bet the answer is going to be 0.200. So up by 3, down by 3. So let's see. We solve for M2 by dividing by V2 on both sides. Plug in the numbers, and exactly what we predicted. So you see how quick this can be. You can even shorten your own solutions for these after a while. All right, now the last topic is going to be properties of solution. And these are real concrete properties that we see all the time, especially in the winter. So here they're putting in antifreeze into a radiator, car radiator. Look what it'll do. It'll lower the freezing point, keep the water in the radiator from freezing. And in the summer, it increases the boiling point, stops the water from boiling over. So we're going to review solutions a bit. So solutions are transparent. They don't separate on standing. They contain small particles, ions, and molecules that can't be filtered. They pass through semi-permeable membranes. They don't reflect light either, so we can't see the particles. Colloids, on the other hand, are very common. These have larger particles. They can't be filtered either, and they are separated by semi-permeable membranes. Now, colloid particles are large enough to reflect light. So if you shine light at a solution that contains a colloid, the solution will light up. You'll see the particles bounce off that. So you could say that the dust in the air is an example of a colloid, because when the sunlight hits streams in through a window and hits the air, you see the dust particles in the air, which you wouldn't see if the sunlight didn't hit them. So we're breathing in those dust particles all the time. So here are some vegetables that they're saying are really colloids. Let's check them out. So see how vegetables look like they're one thing. They're a mixture. Particles dissolved in it have a lot of water. Okay, now next we're going to look at is suspensions. Now suspensions have the largest particles of all, and they settle out because they're so heavy. you can filter a suspension easily and collect those particles. And suspensions have to be stirred usually to stay mixed. So we really don't like suspensions because we always have to stir them up. Think of like any kind of a bottle of a medicine you have that says shake before using. That's really a suspension. Here are some examples here. Blood platelets, muddy water, calamine lotion. Okay. And so here's a chart from your book that compares all three of them, which is good to check out. So this is a slide that's also going to show you the same thing here. So different types of mixtures. So these are all mixtures now. So we have solutions, and it's showing you the little particle here that nice and stay suspended. Colloids also stay suspended, but maybe suspension particles get caught in the filter paper. And here we have a bag, a semi-permeable membrane, and you see in the bag we have solution, colloid, and suspension. And what happens? Only particles that can get out through the bag into the surrounding solution are these solution particles like ions and small little molecules in water, obviously. So here's a quiz for you. A mixture that has solute particles that do not settle out but are too large to pass through a semi-permeable membrane is called a, and what do you think the answer is? It's a colloid. Good. Let's check out some of these colligative properties. Now, colligative property actually means properties that depend on the number of solute particles in solution. So the more concentrated the solution, the greater effect that has on these colligative properties. And so for our solutions, we talk about freezing point lowering and boiling point raising or boiling point elevation. So, antifreeze could also be called anti-boil, and we leave it in the radiator all year long. We don't take it out. And the solute particles disrupt the formation of solid crystals, and that's how they can lower the freezing point of a solvent. Now, what about boiling? Well, for boiling, they also disrupt the boiling point. And so you have to have a higher and higher temperature to keep getting rid of these solvent particles. Here's a prime example. We see this in the wintertime. They spray salt and sand on the roads. Now, sand is not a solute because it doesn't dissolve. The properties of sand is that it's insoluble in water, and you can use that to grip the road. So you want sand on icy roads so you can grip it. But you throw the salts on the road so that you want the ice to melt. So here we use sodium chloride and we use calcium chloride. So the more ions you get from these solutes, the better it is at lowering the freezing point, which really means melting the ice. Now, the calcium chloride is used along with sodium chloride. You get 3 moles of ions in calcium chloride. Now, they don't use that much calcium chloride with it because of the cost. It's more expensive than sodium chloride. If you buy rock salt in a hardware store, you're really buying sodium chloride. You can buy calcium chloride, but they won't sell it by that. They give it a different name. Usually there's little pink pellets. Okay, now we're going to check out osmosis, which is the movement of water from a low solute concentration into a container of a higher solute concentration through a semi-permeable membrane. And if you look over here, the example they have is water on this side, semi-permeable membrane in the middle, and then a water solution, sucrose and water. Now the sucrose particles are too big to get through the membrane. So we actually have movement of water in both directions. But on this side, there's more water molecules lined up on the membrane than on this side, because on the solution side, some of this area is taken up by the sucrose molecules. So what's going to happen? So water is going to move into this solution, and as it does, its concentration will go down, and its volume will go up. Now, will it do it forever? No. What happens? Gravity is going to take over. Gravity is trying to pull the solution in the opposite direction. So we will have water going in here and becoming a more dilute solution. So the sugar can't get out of there. So the movement of water through a semi-permeable membrane is called osmosis. Water always flows into the higher concentrated solution. So osmotic pressure is produced by these solute particles in the solution. And this actually really means the pressure needed to reverse the osmosis. So if I want to push that water back where it came from, it would take some pressure. And so that's what we mean by osmotic pressure. The greater the number of dissolved particles in the solution, the greater the osmotic pressure. All right, let's check out a question then about this stuff. A semipermeable membrane separates a 10% sugar solution from a 5% sugar solution if sucrose is a colloid. All right, so fill in the blanks. Solution A, or is it solution B, has a greater osmotic pressure? 2, water flows initially from which one? And 3, the level of solution of which one will be lower? All right. So the answers are, whoops, I think I missed that. Here we go. Okay, now solution A has the greater osmotic pressure because you're saying from this 5% sucrose solution because it's dissolved in water. If the sucrose was a colloid, it wouldn't break up as much and it's not going to give you that same effect. Water initially flows from B into A, and the level of B will wind up being lower. Because for B, the sucrose isn't really dissolving. That's why that's happening. So B is more like just water. And that's why we get these answers. Okay. Osmotic pressure in blood. Red blood cells have cell walls that are semipermeable membranes. They maintain an osmotic pressure that cannot change or damage occurs. Right? They must maintain an equal flow of water between the red blood cell and its surrounding environment. So we have 3 different types of solutions here. We have isotonic solutions. So here's an example. We see our red blood cells. Isotonic solution, a red blood cell retains its normal volume. Iso means equal. So an isotonic solution exerts the same osmotic pressure as the body fluids, such as red blood cells. So in other words, it's an equal movement of water in and out of the blood cell. So the blood cell itself doesn't really change. So 5% glucose solution or a 0.9% sodium chloride solution are typical isotonic solutions. And this is what they give to people in hospitals, or if they've had an injury, they lost a lot of blood. They give them these rather than just giving them water. Now a hypo means below or less. So let's see what happens in a hypotonic solution. You have a lower solute concentration in the red blood cells. So water flows into the cells by osmosis. The increase in fluid causes the cell to swell and burst. That's called hemolysis. So there's more, here we see the arrow, there's more water flow into the cell than out of it. So we're talking about that hypotonic, a solution concentration that's less than what it should be. And then we have the opposite, which is going to be hypertonic, where you have a solution concentration that's greater. In this case, the cells are going to shrink, and that's called crenation. Water goes out of the cells by osmosis, and we get crenation. Both of these conditions, crenation or hemolysis, of course, are bad. Now, in dialysis, solvent and solute and small solute particles pass through an artificial membrane. Large particles are retained inside. Waste particles such as urea from the blood are removed using hemodialysis, which is an artificial kidney. And you can see what's going on up here. Hemolysis, this is really a summary of what we went over before. You might know somebody that's undergoing dialysis, waiting to get a kidney. Okay, so indicate if each of the following solutions is isotonic, hypotonic, or hypotonic. So you might go back and review the slides here. So we have 2% sodium chloride, 1% glucose, 0.5% sodium chloride, or 5% glucose. And the answers are C, hypertonic. Because 2% is a lot. So you notice isotonic, the only one is a 5% glucose solution, and for sodium chloride it's supposed to be 0.9%. 0.9% NaCl. So if you notice here, this solution is less than that. That's why it's hypotonic. And for the glucose is less than 5%. That's 1%. Sodium chloride is bigger than 0.9%. That's why it's hypertonic. Okay. When placed in each of the following, indicate if a red blood cell will not change, undergo hemolysis, or undergo crenation. Again, you're comparing it to those standard concentration amounts in the blood. Okay, and the answers would be, number 1 is A, 5% is what we want, so nothing's going to happen. For B, 1% is obviously less. We're going to get hemolysis. Cells are going to blow up and burst. And then for B, you're going to have the same thing as too small. And then for C would be crenation. They're going to shrink. And here's a concept mass now of the whole chapter, which you might want to check out. It shows you everything that we covered. So we went from the beginning, what's a solute and a solvent? Took a look at solutes and solubility charts. We talked about saturated versus unsaturated. Then we looked at solutes as electrolytes. You can have strong and weak electrolytes. Strong dissociate 100%, weak dissociate just a little bit, or non-electrolytes which don't dissociate into ions at all. That was all in part 1. And then today we've looked at concentration in terms of percent and molarity, and dilution, so under concentration. Under molarity, we took a look at moles and volume more than anything. And then we ended with solute particles. We took a look at colloids and suspensions a little bit, not much with suspensions though. We looked at colligative properties, which are changes in boiling point and freezing point. And then we took a look at osmotic pressure. And that's it for the show.